Okay, Bergson and the Holographic Theory of Mind, Part 37. We'll be talking about Maxwell, special relativity, and electromagnetism, or the fundamental problem of time and relativity as the supposed theory of time, which supposedly began with Maxwell's laws and the problem in Maxwell, which I think we'll see is rather Einstein's problem. And therefore we'll be looking at the making of Maxwell and Faraday relative, which will lead us to the two SDRs that actually exist, one for Michelson and Morley, one for Maxwell, both two different birds, I think rarely discussed. This leads to the dielectric and the magnetic, which I do not believe can be made relative, and ultimately to the elephant in the room. So without further ado, we'll go into this. So this is a short one. Got a little longer than I wanted it to. I want to tie something together with respect to special relativity and electromagnetism, or so to speak, between my numbers 8a and 8b on relativity and numbers 18 and 22 on Tesla, electromagnetism, and the question, what is a field? So it is not uncommon to see the origins of special relativity couched as such. There was a problem with Maxwell's equations. The implication being Einstein had to correct this problem. Right. The problem is more likely Einstein's, not Maxwell's. And it all goes back quite likely to a rather enormous elephant. It starts with Einstein's first postulate. To paraphrase it, any observer can declare himself at rest and all others in motion with respect to him, and there's no way to say who is correct, which observer is actually at rest. So more technically, the first postulate is stated as, quote, the laws of physics are the same, that is invariant, in all inertial or reference frames. So we have the law, distance equal velocity times time, or in the at rest system, d equal vt, or in the moving system, the prime system, d prime equal vt prime. And it holds in both frames. It's an invariance law, holding in both frames of reference, rest and moving. And the prime, d prime, t prime, just indicates that we need to adjust distance in time units due to measurement differences in the two systems. So this is quite important. This is what we'll meet again, measurement. It's a ruler problem. Who's got the right ruler? This is the key thing we'll meet. So that is to say, all motion is relative. There is no way to tell who is in motion. Or in another word for it that's been lost in current parlance, there is complete reciprocity of reference systems. I can transform the at-rest system to the moving system and vice versa. Reciprocity. Either system can be declared at rest, the other in motion. So no way to tell. But there was an obvious physical phenomenon where the system in uniform motion versus the system at rest can clearly be seen. Of course, to say one is almost absurd, but in physics this stood out. And with the equations which describe the difference, namely Maxwell and the motion of a magnet through a conductor versus the conductor moving over the magnet. And so Maxwell and his equations on the subject. So what's meant here? Well, if you have a stationary magnet and a stationary conductor, as the first picture shows there, you have only a magnetic field. But if you place the magnet in motion through that fixed conductor, the circle with the ring with the C, well, then we get an electric field around the magnet. And there's a nice equation. It's actually Faraday's equation, one of the four Maxwell equations that expresses this. The minus a delta B over delta T is a time-varying magnetic field. The B is the field varying over time. The other case is we put the conductor in motion over the fixed magnet. In this case, what happens is we create an electric field around the conductor. So two clearly different cases in what should appear to be relative motion. Magnet moving through the conductor, or conductor moving over the magnet. But two different things happening depending on what's moving. How can you make this field difference go away? By invoking the relative motion of observers. The difference seems at least intrinsic to or inherent in, remember the word inherent, we'll hit it again, inherent in the ether field to its dielectric and magnetic components. Yet Einstein would add his Lorentz transformation for relative velocity to the equations and make the difference go away. Now, long ago, like around 1974, I made a copy of the relativity section of a physics text. Unfortunately, I didn't write down the name of the text, a bad habit of mine back then. But using my iPhone camera, all the nice available technology, today I can provide proof. And there it is, the picture of the text from my old Xerox. The text starts with the electromagnetic / Maxwell problem as though this is where it all, that is for Einstein himself, started. So let's read. So the Einstein theory of relativity can be derived by forcing Galileo's principle of relativity to apply also to the Maxwell equations of electricity. Galileo proposed as a general symmetry principle that the laws of physics should be the same to any observer moving with constant velocity, no matter what the magnitude and direction of the velocity. And of course, we just noted that in the d equal vt or d prime equal vt prime comment a couple slides ago. In other words, there must be no preferred reference system or no way to determine absolute velocity. This general symmetry principle is called the principle of relativity. Now we're going to see this great liberty being taken with this general principle while calling it special relativity. And no, special relativity, at least the version everyone's familiar with, can't be derived from this, from Maxwell, this case. So continuing, the second paragraph, the text. However, unless some changes are made, the laws of electricity clearly violate the principle of relativity. As we've just seen, an observer at rest and one in motion will get two different answers to the same experiment. Now, warning already, we're not talking in my previous slides of the magnet moving through the coil and vice versa, of an observer at rest and one in motion. But we'll see this later. To illustrate this, we shall consider the simple example of a point charge Q at a distance r from a charged wire. And here's the picture. Point charge Q, the wire vertical up there, distance r of r rho stat coulombs per centimeter. The force on Q is F equal QE. So they're interested in the force on Q there, where E is 2 rho over R, the distance, and is given by an equation we haven't got here. Thus, the force, F, the force, is equal to 2Q rho over R for a stationary observer. Again, stationary observer. So, we're going to go on now, consider a second observer. So continuing on the second paragraph, now consider a second observer who happens to be moving parallel to the wire with velocity v. So we'll put our observer on a rocket to be more like relativity, and he's moving by the static wire there with velocity v. In addition to the above electrostatic force, this observer would also measure a magnetic force. He sees an electric current I equal rho v moving along the wire. So here we have our current. So this is what he sees moving along the wire. This current flowing along the wire, R, I equal rho V, I being the current. And the charge Q also moving parallel to the wire with velocity V. So Q there is also moving. So according to equation 810, which we're not showing, the magnetic force on the charge Q is FB, the magnetic force, equal QV over C times B, the magnetic field. And the magnetic field B produced by a single straight line current is B equal to rho V over CR. Don't worry about too much of this. Thus, F over B, F sub B, the magnetic force, and we give that equation there, noting that the final term is V squared over C squared, and this is the magnetic force. So this attractive magnetic force must be added to the repulsive electric force in the last part of the paragraph, repulsive electrostatic force. Thus, the moving observer calculates the resultant force should be F equal 2q rho over R minus 2q rho over R, and then we have the V squared over C squared form. So that's the force on that particle in the moving observer's case. Remember, for the static observer, previous slide, the force was simply 2q rho over R, and we don't have that nice term being subtracted. So now, given this relative motion, we've added the V squared over C squared there, we can add later on, I'm not showing it here, the Lorentz adjustment, that famous 1 over the parens, 1 minus V squared over C squared, square root thereof, for equal force in each case, the moving case and the static case on that little charge Q. And we're in the special relativity business, according to this textbook. Now this is nice, there's only one problem. This is nuts. Suppose that the wire is just sitting on the table. And so I can just get off the chair, walk by it, and produce a current. Or I can attach 2 wires to a light bulb on my little static wire there. And then I can just tell Felix to walk by, and voila, given he's just walking by that direction there, I get that nice current, I equal rho V. Otherwise, we're getting an alternating current. Creating a current, and the bulb will light because it's that real. Right. This is some strange abstraction sickness that appears to affect relativists. Let's take another example of this. In Andrew Thomas, PhD in physics, in the book Hidden in Plain Sight 3, 2014, Thomas tells us imagine a car pulling a windmill using a rope, like I'm picturing up there. But we'll use Maxwell, the guy called Pig here, driving along with his windmill. Maxwell being appropriately enough named for the subject. With this in mind, says Thomas, imagine you are driving alongside the first car, that is the car pulling the windmill up there, or Maxwell, and you choose a constant speed which precisely matches the speed of the first car. Now as you look at the first car, it no longer appears to be moving. It appears to be stationary. So our car will come up next to Maxwell, and, well, Maxwell's car goes stationary, which means Maxwell, his windmill goes stationary. So Thomas goes on, but as far as you are concerned, the first car has no momentum. It has no kinetic energy. For example, if you have a windmill on your car, like Maxwell did, you can no longer use the energy of the first car to turn the blades of your windmill. The attached line would be slack. So my picture above, the windmill's gone silent still. That line should be slack. Even that car, if I could picture it, would cease to be moving. And so he goes on, so this reveals that the momentum and kinetic energy of an object are completely observer dependent. Right, just like the electric currents in a wire that we just saw. I'm not even trying to do justice to the problems here. It hurts the mind. Once the relativists start claiming real physical effects that is non-measurement effects for special relativity, based simply on the motion of observers, one can have a field day with the logic. But back to the relativization of Maxwell. Could any of this make this go away? I don't think so. So let's take Einstein's 1905 text. To quote, "It is known that Maxwell's dynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena." Of course, the asymmetry is the electric field around the moving magnet versus the electric field around the conductor, the moving conductor. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. So note, he says, do not appear to be inherent in the phenomena. A customary view sees a sharp distinction, but he's saying, no, it's only the relative motion. But the customary view says, yeah, it's motion all right, but it depends on which is moving. There's a difference as to which is moving, what occurs. So yes, there is a distinction. So this paragraph seems already a subtle diminishment of the reality for his own purposes. To go on, for if the magnet is in motion and the conductor at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the places where parts of the conductor are situated. But if the magnet is stationary and the conductor in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force, to which in itself there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the former case. So in other words, yeah, there's a real difference when the magnet is moving, an electric field around the magnet, but we get the same EMF or current in both cases in the coil. So no big deal. I get to say relative motion and erase the difference. But this is a convenient abstraction with no physical model behind it. To continue, examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium, Einstein's word for the ether, suggest that the phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. They suggest rather that, as has already been shown to the first order of small quantities, the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. So in other words, the same laws involving electromagnetism in Maxwell's case and Michelson, Morley in the ether case are going to hold. Now, I don't truly know how he got away with this. Well, maybe we do, but let's do a bit more. The narrative, standard narrative, for example, in Wiki on this special relativity, electromagnetism, Maxwell subject, now it goes like this. In this case, there are two reference frames. The conductor's frame, stationary, magnet moving. The magnet's frame, stationary, magnet being stationary, the conductor moving. To compute the same force on a particle in the coil, in each case, despite the difference in fields, we need to apply the transformation factor, the famous Lorentz transformation factor. Now, note, unfortunately, force on the particle, computing the same force on a particle, was also the subject of the textbook treatment we saw. And what we'll see if you go into the wiki discussion, that Maxwell, we'll see, in that expression minus delta B over delta T, where B is the magnetic field, is already expressing the time-varying magnetic field, B field, moving through the coil. That delta B over delta T is change in time, and gives the induced voltage, that E field there, the voltage, or electromotive force. And wiki, in the link I'll put in the description, titled The Moving Magnet Problem, starts this force problem in the coil's frame, the conductor's frame, or the coil, same thing, by redefining B, the magnetic force field, as B parens x, its position, plus velocity times time. That is x plus vt. It is moving. They start the magnetic field moving, apparently to get Maxwell's time-varying magnetic field moving. This is their move. Now, ultimately, all of this then begins to lead to things like this. The electric field is considered to be transforming partially to the magnetic field, just like space and time are claimed to transform in special relativity from some space having some portion of time, or time some portion of space. And equally, then the magnetic field transforms partially to the electric field. And then this means to them there is really only one field, the EM field, the electromagnetic field. I'll put a link to a couple discussions on this too. Right. Two things. This is not special relativity. Better, there are two special relativities going on here. A Michelson and Morley relativity, M&M, and a Maxwell special relativity for Maxwell's effects. They are not the same thing. Going on with this is not special relativity. The Michelson and Morley special relativity, as we just previewed, there are two observers measuring things in one another's system, one taken as at rest, one is moving, and vice versa, the reciprocity. All effects are measurement effects, like measuring a toaster with two different rulers. One ruler, both the same length, one's 9 inches, and one says 5 inches. We have a difference in units of how big the inches are. So, is the toaster 9 inches or 5.5 inches? It depends on your measurement system. There is no physical, real contraction in this. In the moving system, in theory, according to the measurement, the toaster is contracted, but that's simply an apparent measurement effect. And then remember too, there's the reciprocity. Either system can be moving. The toaster is shrinking in either system, but it's not shrinking. It's a measurement effect. Rather than rulers, special relativity is using light rays and clocks, where the rulers get out of whack, the 5 inches versus 9 inches, because the clocks can be out of sync. It's the same thing, light rays and clocks versus rulers, but they're both the measurement devices. And you have nothing but measurement effects. So in Michelson and Morley, special relativity explained the Michelson-Morley effect, where it seemed that the ether wasn't in motion at all, as a measurement effect. It is, or the Earth wasn't moving through the ether, as a measurement effect. They were trying to measure ether current velocity. And these were observers trying to measure ether current velocity. And it was explained away as simply a ruler problem, a measurement problem. All effects were measurement problems. There was no actual physical length contraction of the apparatus arm, and the light beam was moving back and forth in the direction of the current, parallel to the current, to the ether current. There can be no ontological, no real effects in Michelson and Morley special relativity if it's taken consistently. Attributing via special relativity, real physicality to these effects, like slowed time, slowed clocks, is completely logically inconsistent. It's pure confusion. Special relativity cannot explain them no matter how real the slowed clocks happen to be. It's a theory that can't actually explain it. Something else is needed. Time and length changes compensate for each other in this system. They have to. That's how you get the different supposed proportions of time and length or distance in this system, because they have to compensate for each other. Therefore, they have to be the same order. They have to be measurement effects. This is Michelson and Morley special relativity. None of this is the case in the Maxwell special relativity. In the Maxwell version of special relativity, there are no observers measuring things in the other system or each other system. We have a magnet and a coil. To call these observers is a stretch. They're physical objects experiencing supposedly the same forces if you relativize things. But the magnet is not measuring. The coil is not measuring. There are no clocks and no light rays in use. And really sticky here, all effects are in truth real ontological effects. The EMF in the coil in the conductor is very real, whichever is taken to be moving. Now, all effects are real, but with one exception, I'll say, and that is this transformation of the magnetic field to the electric field and vice versa. But we'll wait on this for a second. Yes, all this was included in the 1905 paper, Maxwell and this problem, and called STR. But the reality, at least two things were going on. This mode, this Maxwell mode of special relativity, is not the same as the Michelson-Morley. It's an effort to make Maxwell's absolute differences due to who is moving based in the ether go away. This is why you can't derive special relativity, the Michelson-Morley version, from Maxwell and this electromagnetic phenomenon, as the textbook promised one could do. These are two different birds. The reciprocal transformation of the electric field to the magnetic field and vice versa has got to be a fiction. Steinmetz, Tesla, Heaviside would have been amused. As we saw Dollar develop it in number 18, the dielectric and the magnetic are in conjugate relationship. Each is the mirror of the other. They are conjugate aspects of the ether. It's not possible for aspects in such a relationship to reciprocally transforming into each other. The math works, supposedly, but deeper understanding of EM has probably ceased. As Dollar argued, further development of electromagnetism has effectively been halted. So there's a myth that Einstein started with Maxwell as a pure theoretical interest. The reality, he started with Michelson-Morley. Maxwell, he knew, was an obstacle to his solution. To quote from a speech he gave in Kyoto, Japan, "Soon I came to the conclusion that our idea about the motion of the Earth with respect to the ether is incorrect, if we admit Michelson's null result as a fact. This was the first path which led me to the special theory of relativity." But there's an elephant still in the room. Due to Michelson and Morley, plus Sagnac's experiment, plus Airy's experiment, Airy's failure it's called, plus several more by Michelson, which people don't know about, the Earth was stopped, stone still. Physics, it seems, was desperate to get it moving. The implications of this stopping stone still of the Earth for our real understanding, enormous. Did Einstein and special relativity actually get it moving again? I don't think so. I certainly haven't done justice to the complexity here. Is Maxwell the end-all in electromagnetism? A correspondent friend of mine just noted for me that Tesla, Dollard, did not think so. He also pointed me to Yang of Yang-Mills theory, which is a gauge theory, and noted that Yang started with Maxwell, attempting to reconcile quantum mechanics wave equation and special relativity. So here we have extreme complexity. But there's still always the fundamental question, never addressed. Which special relativity are you reconciling to? The logically consistent, in which all effects are measurement effects? But then why? Why the reconciliation? If all effects are unreal, what good does it do to reconcile it in the first place? Or secondly, the logical mess, the half relativity, where time retardation is real, but length effects are not, and where we simply ignore reciprocity. Or three, as we've just seen, or there's Maxwell's special relativity, which is neither one nor two, but another bird completely. I've never seen a physicist who isn't actually using two, or maybe three. There is complete confusion, even mind programming here. In duration and simultaneity, Bergson, to my memory, did not address the Maxwell aspect in his analysis of special relativity. There could have been many reasons. Basically, his prime focus was the logical mess of the twin paradox, which turned time retardation from a measurement effect into a real ontological effect, a very real aging of the old twin left behind versus the young twin riding on a rocket. One thing is clear. He laid out the logical structure underlying special relativity's, quote, explanation, unquote, of Michelson and Morley. That is the true structure of Michelson and Morley relativity, as we'll call it, so clearly it makes the stark difference with Maxwell relativity easy to spot. Just yet another problem with the mess that is relativity. And another thing is clear. Again, as a theory of time, special relativity, quote unquote, whatever version, can have no status whatsoever. So down the road, I've got a list of 15 things or so. Some of the things I'm thinking about: Bostrom and his superintelligence book, Whitehead and Bergson, Searle's theory of seeing, quite an interesting attempt to make a direct realist theory. Physics and the holographic principle is still interesting. Quantum mechanics, origin in the black body phenomena, and Piaget's attack on Bergson, also other things, or something that strikes me, which is kind of the way I'm going at this point. So next time we'll see. Until then, signing off.